This is the second video in my series of project showcases. Today I'm going to be talking about the binomial machine, which you can see I've titled here twice, slightly off-center for some reason. So the binomial machine is of course all about binomial distributions. So if you don't know what that means, you can check out a video I have in the description that I made about binomial distributions, or you could go research it yourself somewhere else. But if you do know what it means, you can keep watching. I had this idea for a sort of binomial distribution visualization tool when I was taking AP Stats in high school, and I learned about the binomial distribution, and I thought it was pretty interesting, and I also thought I could experiment with it with code. So the first obvious feature is that we graph this histogram, the blue rectangles of an exact binomial distribution. And we also have this red sort of bell curve, which is a normal distribution that approximates the binomial distribution. And we'll see later that there are certain factors that make that normal approximation better or worse. But for now, you can see it's doing a decent job of following the rectangles. So here we can see that the values of our two parameters are n equals 10 and p equals 0.5, which is saying that there's 10 Bernoulli trials and a 50% chance of success on each Bernoulli trial. You could conceptualize this as there being 10 coin flips and a 50% chance of getting ahead because it's a fair coin, and our output is the number of heads we get, right, the number of successes. So the most likely outcome, of course, with about a 25% chance of occurring, is that x, the number of successes, equals 5. So that's 0.24609 probability, or around 25%. You can see also that this graph is symmetric, right? And that's because heads and tails are pretty much equivalent because the probability is 0.5. They're sort of interchangeable, right? So you can see that 4 heads and 6 tails is almost the same thing conceptually as 6 heads and 4 tails. They both have around a 20% chance of occurring, 20.5. The least likely outcome is, of course, getting 0 heads or 10 heads. That has a less than a 0.1% chance of occurring because you'd have to get the same flip every time. So that's 1 over 2 to the 10. If we look on the right here, we can see that if we left-click a bar, we can see some advanced probabilities, which means if we left-click this 4, for example, it tells us what we already knew. Probability of x equals 4 is around 20%, but also now this new probability, the probability of x being less than 4, is around 17%, which is just these bars added together, 3, 2, 1, and 0. If you did that by hand, you'd have to manually add them together. So the fact that it's just given to you here is pretty nice because it's a common need for a binomial distribution. You need to know something being less or more than some value. You also have less than or equal to 4, which is just these first two values added together. The probability of x being greater than 4, which is just these bars, 5, 6, up to 10, added together, and the probability of x being greater than or equal to 4. We can also right-click some bars, as it says here, to see the probability over a range. So for example, we can see the probability between 4 and 7. And you can see that gives us the output, around 77%, but it also gives you the output for using the normal approximation. And you can see the values are pretty close. So that means this normal approximation is doing pretty well. So to get the approximation, that value from the normal distribution, you could integrate under the normal distribution, right? Because it's continuous, instead of just summing over the values of for the binomial distribution, you have to integrate over this curve, under this curve. Now, if we change the probability, so let's say 0.0 to 0.05, so that's 1 in 20 chance. So we could say this is like rolling in Dungeons & Dragons. You roll a d20, and you need a 20 to pass something. Then now the most likely outcome is actually 0 successes, because success is so unlikely. And you can also see now that this normal approximation is pretty far off from the actual rectangles. So if we look again for this range sum, the normal approximation is actually pretty far off from the true value. It's almost 10% off. That's not great. So you can see when we skew this p-value, this probability, the approximation becomes worse. The approximation will become better if we increase this n, right? Let's say we do 50. So now there's a lot of trials. So that would be like rolling a lot of t20s. And now that red normal curve approximation becomes pretty close, decently close to the blue histogram. It'll become even better if we recenter the graph by using p equals 0.5. And you can see now that's starting to become a pretty good approximation. The red curve is following the histogram pretty well. And it'll become even better if we increase n even more. It takes a little longer to load, but it gets there. And now this is you can see this is a really good approximation. The red curve is almost exactly following the histogram. And we can still do all the same things, like seeing all the advanced probabilities, or summing some probabilities over a range. Like that. So you can see that approximation is pretty good. We can also simulate trials. So let's reset the parameters back to the default values so it'll run a little faster. And we can perform a simulation, which means if we do one simulation, that means we're doing this series of Bernoulli trials and counting the number of successes. So let's do one of those, and we see we got the most likely outcome of x equals 5. If we do another, we get x equals 6. That makes sense. X equals 6 is also pretty likely. X equals 7, and we get another 6. And we can keep simulating. As you can see, we're getting mostly the more likely ones, and more of the more likely ones as well. But the idea is, in statistics, there's this concept of the law of large numbers, which means as the number of simulations we do, or the number of samples we do, converges to infinity, as it goes to infinity, our distribution, or just in general, whatever value we're measuring, should converge to the true underlying parameter value, which is this blue exact binomial distribution. Which means for us that if we do a lot of simulations, so now we're doing 10 at a time, and we're up to 290 total, as you can see, that this histogram should become very close to this blue histogram. And you can see it does. So for a while, 6 was leading, which goes against our exact binomial distribution, but that happens with random numbers. But as we simulate more and more, that went away, and now we have a graph that's pretty close to the blue histogram. We can also clear the simulations and start again. So let's see what we get the first time here. And this time is actually 3, which is a little unlikely. But again, as we do more, every time, it will slowly converge. You can see 5 is still behind, but we've only done about 50, 60 trials, 70 now. And if we can start doing 10 at a time now. And slowly, 5 should catch up. Sometimes you have to do more trials. But we could even do 100 at a time. It'll really match it in the end.